Hi everyone, and welcome to another example problem video. In this video, I will be covering how to solve an optimization problem. And I've already put out, as you can see in the top left corner, the list of steps that you need to follow in order to solve any standard optimization problem. Also, in the top right, I have put up a reminder that I'm going to leave up there about what the word critical point means. I like to think of critical points as being flat points, that means points where the derivative is zero, or spiky points, which means that the derivative does not exist. I think it's always useful to keep in mind as you're working through these problems what the points that you're looking for actually look like on the graph. Okay, so the example problem I want to cover today is pretty straightforward. It's asking you guys to find the local maxes and mins of the function f of x equals x cubed minus 2x squared plus x minus 2. Okay. So as I mentioned, I've already listed, and I will be leaving up in this top left corner of this video, the 3 key steps that you need to follow in order to solve any optimization problem. Whenever you're asked to find the local max, or min, or both, of a function, you need only follow the following steps. First, find the derivative of the function that you are working with. So let's do that right now. This is pretty straightforward. Step 1, find f prime of x. In this case, we just have a very straightforward power rule. This x cubed becomes a 3x squared. This minus 2x squared becomes a minus 4x. And this plus x becomes a plus 1. That minus 2 becomes 0. That's it for step 1. Okay. Step 2 is the key part of any sort of optimization problem. And the step 2 is going to be to find the critical points of the function f of x by using this derivative that you've just calculated. Now, this is where the reminder that I've put up in the top right corner of this video comes into play. When we talk about finding critical points, that means that we're finding points where the function is flat or finding points where the function is spiky. In other words, we're looking for when the derivative is 0 or when it doesn't exist. So the first and sort of key step involved in any of these optimization problems is going to be to solve the equation f prime of x is equal to 0. In this case, we have just calculated that f prime of x is equal to 3x squared minus 4x plus 1. We are setting this equal to 0, and we are trying to solve. Okay, there are multiple different ways to solve any quadratic equation like this, but there is one method that always works, and so I recommend that you just learn this one, and this is to use the quadratic formula. Now, quadratic formula states the following. If we identify each of these coefficients, this first one as a, this second one as b, and this third one as c, then quadratic formula tells us that our solutions are going to be equal to negative b plus or minus the square root of b squared minus 4ac, all of this divided by 2a. Let's put this out here in the corner so that we have more space to write this out. So substituting everything in here, we see that b is equal to -4, therefore negative b is equal to 4. We have a plus or minus, then we have a square root. B squared is 16, minus 4ac is 4 times a 3. C is equal to 1, so this is 4 times 3. All this divided by 2a is divided by 2 times 3. In other words, this is going to be 4 plus or minus the square root of 16 minus 12. All this divided by 6. Square root of 16 minus 12 is the square root of 4. So this is 4 plus or minus 2 divided by 6. Now, if you do plus 2, we get that x is equal to 4 plus 2 divided by 6, which is equal to 1. If you do minus 2, you get that x is equal to 4 minus 2 divided by 6, which is equal to 2 over 6, or in other words, 1/3. Okay, so that was that. We have now solved the equation f prime of x is equal to 0. We have found that the solutions are x equals 1 and x equals 3. So these are our two critical points. Okay, before we move on, it's always important to ask yourself, the following question. Is f prime of x undefined anywhere? If yes, add those points to the list of critical points. Okay, always make sure that you ask yourself this question before moving on, because it's very easy in my experience to forget that critical points can also be spiky points, in other words, points where the derivative fails to exist. Now, just always do a quick double check before you move on. Did you miss any critical points where the derivative doesn't exist? Now, in many cases, including this one, it's pretty easy to tell that here there are no such points. The curve f of x is equal to x cubed minus 2x squared plus x minus 2 is nice and smooth. It does not have any spiky points. Its derivative is defined everywhere. Okay. These first two steps are the crux and the key points of any optimization problem. Once you have gotten to the end of step 2, you have done almost all of the work. In fact, some optimization problems stop here. They do not actually ask you to find the maxes or mins. Some of the problems in the book will just say find the critical points. And if that's the problem that you're solving, then at this point you are done. Now, of course, in most problems, including this one, you will be asked to go all the way to the end and figure out what are the local maximums and or minimums. So let's do that now. Okay, let's move this a little bit more out of the way. And this may not seem like much space, but it should be more than enough for step 3. Step 3 is very straightforward. What we're going to do is check each critical point. to see if it is either a max and a max is a point at which your function before it is increasing and afterwards is decreasing. Or a local min, which is a point where prior to it you are decreasing and then afterwards you are increasing. If your function does not change direction at that critical point, then you have neither. So if your function goes up before and is still going up afterwards, your critical point is neither a local max nor a min. Same thing is true if it's going down and still going down. Okay, there are various ways of doing this. All of these lead to Rome. You can check the textbook to see or read more about the first derivative test, about the second derivative test, but my general solution, which is very, very straightforward, is just graph it. And if you graph this function, it's actually quite straightforward. Actually, it's worth pointing out, graph it, by which I mean graph the function f of x. Not the derivative, graph the original function. If you graph the function that we have here, you'll see that it looks very vaguely as follows. So along this graph, our function is going to be going up, then back down, and then back up again. And it's very easy to note that this point here is going to be a max, and that this point here is going to be a min. Now it's very easy to identify which one of these this is, because the one that comes first is obviously going to be at x equals 1/3, since that is the lower value. And the one that comes second is going to be x equals 1. And you can see again what I meant when I said that local maxes are increasing before, decreasing after, and local mins are decreasing before and increasing after. Okay, that's really all there is to these optimization problems. Now, obviously, every optimization problem is going to look a little bit different, but these 3 steps will always be the same. The actual process of doing step 1, finding the derivative, will change. Depending on the function that you are asked to optimize, the derivative itself may look very, very different, or may require you to use different rules. But step 1 is always just to find the derivative problem, and I've covered how to do that in other videos. Step 2 is not a calculus problem at all. You've already found the derivative at this point, you already know what f prime of x is, you just set it equal to 0 and try to solve that equation. In this example, we needed to use quadratic formula, or some other tool for solving quadratic equations. You might not always get a quadratic equation here. You will always get some kind of equation that you need to solve, and you're going to have to use your tools from algebra to do that correctly. Step 3 is to just check each of the different critical points that you found and see if each of those is either a local max, a local min, or neither. There's lots of ways to do that. Again, you can check the textbook for the first derivative test and second derivative tests if you wish. But I always recommend just graphing your function. It doesn't have to be a very precise graph. Just look at what it looks like on your graphing calculator or punch it into a computer. And it's very, very easy to tell whether the points that you're working with are maxes or mins. Okay, I don't think it's worth going over another problem about this because, again, these steps are always going to be the same, and each of these is itself a problem that you've already covered either in this course or in a previous one. However, I do think it's worth doing one sort of comment before leaving you guys with this video. And this is if I ask you guys a slight variation of this problem. What about inflection points? Finding inflection points is exactly the same thing but with the second derivative. It's very straightforward. Step 1 is going to be to find a formula for f double prime of x. Step 2 is going to be to solve f double prime of x is equal to 0. And step 3 will be to identify does f of x go from concave up, which looks like an upward shaped U, to concave down at that point, or vice versa. And once again, to check this out, you can simply graph the function and look at it. This is all that's involved with finding inflection points. It's basically, in fact, it's literally the exact same process, except instead of looking at the first derivative, as you do in the steps for finding local mins or local maxes, you look for the second derivative. You find that second derivative, you set it equal to 0, you solve that, and then you double check, does the concavity change at that point? If so, you've got an inflection point. Okay. Try not to confuse these two. If everybody needs me to, I'm willing to make a separate video on finding inflection points. But for now, I think it's just very straightforward. It's almost identical to exactly what we're doing when you're finding critical points and local maxes and mins. So I'll just leave it at here for this video. I know this one was short, but like I said, all of the steps in these problems are steps that you've seen before in other problems and that you should be relatively comfortable with. And this is pretty much all I have to say about this.